Perovskite solar cells. Welcome to D Creations Resources. Let's talk about perovskite solar cells. Perovskite is named after the Russian mineralogist whose name was Perovsky, and basically it has a specific crystal structure. The formula can be ABX3, where X is usually oxygen or halogen. A stands for a larger cation which occupies cubo-octahedral site, which is shared with 12 X anions, that means either halogens or oxygen, while the smaller cation, which is B in this formula, is stabilized in an octahedral site shared with 6 X anions, where again X is oxygen or halogen. The most studied perovskites are oxides usually because of their electrical properties being very interesting in terms of ferroelectricity or even superconductivity for that matter. Now, the first perovskite that was studied was CaTiO3. So here you can notice that its calcium is the larger cation, that stands for A. Then titanium stands for B, and allied here X is basically oxygen. Similarly, many people also study BaTiO3, barium titanate, another famous example of perovskites. The high optical absorption and direct bandgap property of perovskite semiconductors make it superior than the first generation, for example silicon solar cells, and second generation, for example gallium arsenide solar cells. The main interest in perovskite solar cells was due to a sudden increase in its efficiency. So in 2009 the efficiency was reported around 4%, and that increased to around 16% in 2014. When we discussed the formula, general formula for perovskites ABX3, we mentioned that A is a larger cation. Now it can be organic as well as inorganic, but B usually, which is a smaller cation, is usually a heavy metal. Now it is obvious that if people have started thinking of these newer materials instead of the conventional silicon or thin films based on CDT, etc., they must be having some kind of advantages. So efficiency is a huge advantage, as mentioned just now. Also, the fabrication methods are usually low temperature and solution based, so way easier as compared to say wafer based technology. The absorption coefficient is high, and they are also very stable in air. And the open circuit voltage VOC, we have studied the IV characteristics in which we had looked at VOC. That also is very high for these solar cells. And there are high charge carrier mobilities. That means the electrons that would be generated as a result of photovoltaic effect on incidence of photons. These electrons and holes, they can move larger distance instead of losing their energy as heat within the cell. Now there is one more advantage with respect to fabrication. You can also print it on flexible substrates, because nowadays there is a huge demand for flexible solar cells, and perovskite solar cells can be a very good option for that. Now perovskites have a distinguishing crystal structure. The B part in the formula ABX3, the B cation, it's at the center. Then imagine a cube, and A will be at the vertices of this cube surrounding this center, while X halogen will occupy the face centered positions. So you can imagine a cube at the center of which there is B cation. Then at the vertices of the cube, cation A is present, while halogen X will be at the face centered positions. Now note that X can also be an oxygen atom, but here in this case usually it's a halogen. So the perovskite structure, you may have studied BaTiO3 for example. So if you recall, in case of BaTiO3, how the structure was. Now similar logic is followed even here. Now there is a parameter called tolerance factor, and it is basically a measure of the degree of distortion of a perovskite from the ideal structure. What was the ideal structure? It was cubic, but there could be some distortion, and that is measured by tolerance factor, usually denoted as T. There are sensitized perovskite solar cells. In these, the active layer contains a layer of mesoporous TiO2 which is coated with perovskite absorber, and this active layer is contacted with an N-type material for electron extraction and a P-type material for hole extraction. While there are also thin film perovskite solar cells, in these there is a flat layer of perovskite which is sandwiched between selective contacts. Perovskite solar cells, part 2. So welcome to Decreation's Resources. We have looked at what perovskites are and certain features, their advantages, their comparison with silicon solar cells, etc. Now let us see the fabrication part of perovskite solar cell. So if you have a look at it, a typical generic structure of planar perovskite cell, then you would see that at the bottom there is a layer of TCO, on which there is electron transport layer, on which there is active layer of perovskite. Then there is hole transport layer, and above which there is electrode. Now if it is inverted NIP, same structure, but instead of hole transport layer you would have an electron transport layer, and vice versa. Now a perovskite film is typically processed by either vacuum or solution method. So film quality is very important. Typically the active layer of a perovskite solar cell is deposited via either a 1 or 2 step process. In the 1 step process, a precursor solution, which could be a mix of CH3NH3I and PbI2, is coated, that then converts to the perovskite film upon heating. A variation on this is the anti-solvent method, in which the precursor solution is coated in a polar solvent and then quenched during the spin coating process by a non-polar solvent. Now precise timing of the quench and volumes of the quenching solvents is required to give the optimal performance. There could be a range of series pumps which can be used in this kind of a process. Now in the 2-step process, the metal halide, for example PbI2, and organic compounds, for example CH3NH3I, are spin coated in separate subsequent films, and alternatively metal halide films can be coated and annealed in a chamber filled with organic component vapors, which is called vacuum assisted solution process, VASP. Most of the state-of-the-art perovskites are based on a transparent conducting oxide or ELT or perovskite structure, where ELT is basically electron transport, and similarly we also have HTL, which is hole transport layer. Typical hole transport layers could be some polymers, and typical electron transport layers could be TiO2 or SnO2. Understanding and optimizing the energy levels and interactions of different materials at these interfaces is very important. Typically, what is the thickness of this layer? Because you know that the thickness of an active layer is important. Here it could be several hundred nanometers thick, the perovskite layer. So now we know that perovskite or perovskite structure is basically, the terms can be used interchangeably, but a perovskite is a type of mineral that was found long back in Russia and Ural mountains, and it's named after the person Perovsky. Any compound which has the structure similar to this mineral is said to have a perovskite structure, and typically the true perovskite, the mineral, the original mineral, contains calcium, titanium and oxygen, and its formula is CaTiO3. The generic form is ABX3. So in case of CaTiO3, A is Ca, B is Ti, and X is oxygen. We've spoken about its structure. Imagine a cube, and in case of perovskite with the generic formula ABX3, A is the cation, that means it's positively charged, and it is at the center of the cube. The corners of the cube are occupied by B, which is again positively charged cations, but smaller ones, and the faces of the cube are occupied by smaller atom X. It's a negative anion. It's a negative charged ion, so that means anion, and it could be oxygen as well as any halogen. A could be inorganic or also organic cation, for example, methylammonium, CH3NH3 plus, or formamadinium, that is NH2CH NH2 etc. While B is inorganic cation, lead is preferred, Pb2 plus. Though of course lead has its own toxicity issues, so there are efforts to replace lead with other cations with similar properties. And X we already spoke about. It's a halogen anion usually, like chloride, Cl minus, or iodide, I minus, etc. Typically, if the perovskite is to be used for applications pertaining to its ferroelectric properties, etc., then an oxide is preferred, but here a halide is preferred. There are some disadvantages for these solar cells, like the film quality. It's not very easy to maintain it, or obtaining the thickness, etc. But there are advantages about the flexibility, about the efficiency, which has been increasing at a faster rate, etc. So it is slowly trying to replace the first generation, second generation solar cells, though right now it's more in the research stage, so it will take some time to completely replace it.